Hi. I hope this is working. I can see some of you guys showing up. How's it going? Looks like it's live. Looks like everything's coming along. Happy Wednesday. It's Wednesday. It's always Wednesday. I only see you on Wednesday. Oops. Hey Sky, how are you today? Glad you guys are here. If you showed up earlier, I'm trying out this new thing. I've been playing with the way we set this up. I tried this so you guys could see what it was. Sky asked, are there more chapter 5? Yes, they will go up on Friday. So if you look at the syllabus, the schedule on the syllabus, the rest of chapter 5 will get posted on Friday. So this week is end of 4, beginning of 5. Next week is the rest of 5. The week after that is 6. And then the exam? Yes. So for the remaining 3 sections of 5, there are 3 videos. They will go up on Friday. And they will go with the rest of the notes. So, good question. Any other questions before we get started? Nothing. I don't have a whole lot. Well, I have like 9 questions, so I guess I have a lot today. Other questions. The weekly assignment will go live later today. It will cover material from today's video. So far, it looks like you guys are showing up, hanging out. It's very exciting. Are there any topics from the videos that you guys are like, whew, those were hard, wish there was more? The oxidation numbers and activity series, we're not going to talk about a lot today. There are a lot of examples in those videos. You will mostly see that material covered in lab. So you should use that in that case. All right, doesn't look like we're getting a lot of other questions. So we are going to start today with the chapter 4 material, which is titration. So we have 4 examples from that, and then 5 examples from the beginning of chapter 5. As always, this is not indicative of everything you will need to know for the semester, just something. So in our first example, it asks how many grams of calcium hydroxide are needed to neutralize 97.21 mils of 1.25 molar nitric acid. So the first thing we need to do for all of the titration type questions, the number one thing you need to do is write a balanced chemical equation. So balanced chemical equation is going to tell us how to set this up. So in this case, we have calcium hydroxide. So calcium is Ca2+, and the hydroxide unit is a -1. So we have calcium hydroxide that is solid and soluble. Is going to be added to nitric acid, HNO3, aqueous. And because we know this is an acid-base neutralization, our products really only are going to be it's going to be 2 things, a salt complex and a water compound. So we have H2O, plus in this case, our anion is nitrate, the cation is calcium, so we know we're going to get calcium nitrate. All nitrates are soluble under every condition known to man. So that's going to be aqueous, which means we need to check for balanced. We have 2 nitrates on this side, so we're going to put a 2 here. 2 hydroxides, 2 protons gives us 2 waters. And this actually comes out as a liquid. So now we have a balanced chemical equation. First step, Done. Next step. It asks how many grams of calcium hydroxide are needed to neutralize. And at a neutralization point, the moles of acid equals the moles of base. So, or their equivalencies. So in this case, we're going to convert nitric acid to calcium hydroxide, both through the molarity and through the stoichiometric coefficients. So we're going to take our 1.25 molar and split the units into 1.25 moles divided by 1 liter. Let's make that decimal point something you can actually see. So in this case, our 1.25 molar is 1.25 moles divided by liters. So from here, we're going to multiply that by the volume that we used in liters, 0.09721 liter. So when we plug this into our calculator, you will get 0.12054 moles of HNO3. Let's just, I'll move that back in a second. So now we have the moles of nitric acid. So the next thing we need to do is to convert that into the moles of calcium hydroxide. So for every 2 moles of HNO3, that requires 1 mole of calcium hydroxide. So when we plug this into our calculator, you should get, I don't know, so I didn't stop there. So for every 1 mole of calcium hydroxide, and I don't think that's on the camera, it's 74.01 grams. I'm so sorry. Not my best day. But that didn't help us at all. So from here, we converted moles per liter, multiplied by liter, got moles. Use the stoichiometric coefficient. So this is from the balanced equation. This is our molecular weight. So when we write that, plug all this into our calculator, we get 4.466 grams of calcium hydroxide. And based on the number of sig figs in the problem, we should actually only have 3. And so the number of sig figs here is going to be 4.47 grams of calcium hydroxide. So when we think about this first question today, what questions do we have? As always, if you have none, you can go ahead and drop none in the box so that I know. But as we think about this, this is what I would consider a basic titration question. It's really just the same as in Chapter 3, Part 6, where we talked about using balanced chemical equations. We've just changed from grams into milliliters of some concentration. So what do you guys think? What questions do we have? How does this feel? And I will move out of the way so you can see the work. Ooh, thanks for commenting, Kachal. Whoops. I think, so Camilla, maybe, mentioned that I made a small math mistake, which is here, so we'll just fix that here, which I think you still get all of the right answers. The same answer, you can plug it in later. So it sounds like we're moving along. So let's look at the second question. And let's try to make this a little bit less even, because frankly, which kind of makes it crazy. So it asks how many mils of hydrochloric acid are necessary to neutralize 145 mils of 1.49 molar strontium hydroxide. So as I start erasing the board, think about the balanced chemical equation, because we're going to need that. So in this case, as we think about the balanced chemical equation, so you might be like, how come on most of these we're not giving chemical names? If you looked in the slides or in the video, you are responsible for knowing the strong acids. Anything else, I will provide it to you and tell you what the protonation or basic units would be if I pick something obscure and not one of the known. So our first thing is that we have HCl is hydrochloric acid plus strontium hydroxide. And so together we're going to get strontium chloride and water. So strontium is a 2+, so we have strontium with 2 chlorides plus H2O, which means we need to drop a 2 here and here. So usually this is how your equations balance, so it's less important for you to have the states in here, unless on the exam I ask for that. But most of the time, it won't ask for that, so you just need a balanced equation. So once we have a balanced equation, now we can start to do math. So a titration question asks, or in this case, a neutralization, at what point are these two equal? That's what happens at neutralization. So in this case, we're going to take our 1.49 moles in 1 liter and multiply that by 0.145 liters, which this is going to give us, hopefully I did this math correctly, 0.21605 moles of strontium hydroxide. Then we're going to convert that into moles of hydrochloric acid. So from here, for every 1 mole of strontium hydroxide requires 2 moles of HCl. And this gives us 0.4321 moles of HCl. So the question asks how many milliliters of this concentration, which is slightly different than some of the other ways we can start to think about that. So this is not asking for the concentration of this. We have that. I want to know what volume we used. So from here, we're going to take our 0.4321 moles of HCl, and then we're going to use the molarity, but we're going to invert it so you can divide by the molarity. And so what we'll get is 2.34 moles in 1 liter. It does ask for this in milliliters, so we're going to go ahead and drop that calculation in there. In 1 liter, there are 1,000 milliliters. And I get 184.65 milliliters, which using our 3 sig figs is 185 mils. So what questions do we have? Did I make any math mistakes? Which I hope not. So if we have no thought, if you're like this, we're on board, let me know and we'll move to the next one. So there are some trickier. I did pull some from what I think are the more difficult ALEX objectives. Those are coming up. So what do you guys think? So Kajal asks, I'm going to answer Kajal and Mariah's questions together. So Mariah, the 2.34 is the molarity. I think I'm pointing to the right thing. I don't actually know. It looks like the right thing on my screen. So this 2.34 molar is the concentration of hydrochloric acid. A lot of times we solve for the something else. For the molarity, so you would have been given a volume. So Kajal asked, do you have to split these? You definitely don't. So you can leave this as molar. You can basically divide by molar. I split it out so that I make sure that I follow my units. So if you definitely don't have to. I always show more work than you need. And so in this case here, you can basically split it or not. It's up to you. I do it for clarity. So Camille asked, can you go over it one more time? I am confused by the conversion. Yeah, I am happy to go. I don't want to say 100 times, but let's look at it again. So the question asks, how many milliliters of 2.34 molar hydrochloric acid are necessary to neutralize 145 mils of 1.49 molar strontium hydroxide? So this here is our initial concentration. So all I did was take molar, which is the big M, and split it into moles over liter so that I could multiply and divide as I wanted to. This is our starting volume in liters. So I took 145 milliliters, converted that to liters. So we now took our moles per liter times liters, and that gives us the moles that are found in that volume. So from here to here, it should look just a little bit like the stuff that we did at the end of chapter 3, right? Where we started with grams and converted to grams. So instead of starting with grams, we started with a volume and a concentration. So here we have the number of moles. So now I used my balanced chemical equation. So this just says that the stoichiometric coefficients, and if you're like, what does that word mean? It's the big numbers in front of anything on a balanced chemical equation. So in the balanced chemical equation, we have a 1:2 molar ratio, so 1 strontium hydroxide for every 2 hydrochloric acids. So now we've been able to determine the moles of HCl. Now, this part down here is a little bit tricky. So oftentimes when we think about titrations or neutralizations, we are solving for the molarity of the acid, like we'll see in 2 questions from now, in number 4. But in this one, it asks for the volume. So we can use the molarity of the sample to determine the molarity of the acid to determine the volume. So if we have moles, we can use the molarity. So this is our molarity. And then the moles would cancel out. We'd have liters, and then we convert it into milliliters. So what questions, and I personally have taught this class a long time, and I think that titrations and limiting reactants are really hard. And I think what makes them hard is there's a lot of steps, and you have to keep track of a lot of things. So, Camille, what questions do you still have? And if you don't have any, feel free to drop none in the box. Does anybody else have different questions about this question? Where's my marker? while we are waiting, I will go ahead and plop the next one up. So if you are good on this question and you haven't already tried to solve this, why don't you go ahead and do that? I will try to get out of the way so you can actually see it. Sweet. Yay! Y'all, it makes me real happy when you say that like you understand stuff. Just bright spot in my Wednesday. So in our next example, we have two other questions coming in hot. So we've been asked, can we use M1V1 equals M2V2 instead of changing the units? No. So M1V1 equals M2V2 works really well for a dilution. For a titration, if you had done that in this question or the previous question, you would have not gotten the right answer. You would have been likely off by a factor of 2, either dividing or multiplying. So in this class, it will never be a 1-to-1 acid base. So like HCl and sodium hydroxide. It's 1-to-1 base to acid. So you need to be able to convert using the molarity in this case. So you can use that. You will get the wrong answer. Doing it this way will get you to the right answer. If you're going to do one of the convoluted ways where you use M1V1 equals M2V2 and then add in the stoichiometric coefficients, I'm not quite sure how that's different than the method that we just showed. And that method will get you the right answer. Some of the others don't. So Holly asked, are they always going to be strong acids and bases? In this case, in a titration in my class, yes. Titrations with weak acids and weak bases, you will see that again in Gen Chem 2 if you're going to take that. If you're not, then we're going to just mostly only talk about strong acids and strong bases. So a weak acid only slightly protonates, so we're really not going to encounter those in this class. If I tell you, let's think of that a different way. If in a question, it will always fully protonate in a titration. So you are not going to worry about, there are some coefficients and some rate constants that you might have seen in other chemistry classes that you've taken. Those don't exist to us here. I hope that answers your question, Holly. So on number 3, it says, suppose 1.47 grams of iron 2 iodide is dissolved in 200 milliliters of a 24 millimolar solution of silver nitrate. What is the concentration of the iron ion in solution? So this question is adapted from one of your ALEX objectives. This one is often one of the objectives where students are like, I don't understand what's happening. So if you get to this objective in your objectives and you're like, oh, I don't remember, feel free to come back to just this part. Hopefully it'll help you. But you should also have some notes. So you will see this a lot, and we'll solve this one, and then I will tell you the things to look for in the future. So the first thing we're going to start with is a balanced equation. What else will we start with? Come on. So we have FeI2, which is coming in hot as a solid. We're going to dissolve it into silver nitrate, which is aqueous. So then we're going to, because this is a metathesis reaction, we're going to play do-si-do. So we're going to swap our partners. And so we're going to get FeNO3 plus silver iodide. And we're going to go ahead and balance this, so we're going to drop some 2's in here. Now, this is a combo meal. So Combo meals in my class are things where we're going to use two different topics to solve the same question. When you think about this, you should be like, I wonder if that silver iodide is soluble or insoluble. So it turns out there are two things we need to think about. Is iron iodide soluble? And it is. So when you drop this into the silver nitrate, it is going to dissolve. Then the question we have to answer is something going to precipitate out? So in this case, all nitrates under all conditions, 100% of the time, are soluble. Okay, well, that's great. Aqueous. But it turns out that iodide salts are insoluble when they're mixed with silver and a few other things. So this is going to be solid. So I tell you all of this because in these questions, you'll see a lot of them. You're going to have to write a balanced chemical equation. Done. Check. The next thing we're going to have to do is limiting reactants. But not always. So, because it's asking about the iron ion in solution. But the iron ion is going to be in solution at the same concentration that it was here. So whatever you put in is not going to be affected by the limiting reactant because it is soluble. So we know that the iron ion on both sides is soluble. So this, what I'm trying to tell you is that your answers, it may involve a limiting reactant. It may be that it's 0. So if in this case the iron was the limiting reactant, there would be none left over. If it wasn't the limiting reactant, you might have to do some subtraction. These are not the hurry up objectives or the hurry up like types of questions. They'll take you a little while, but it will refresh you from limiting reactants. So now we know that iron is soluble on both sides. So the question asks, what is the iron concentration at the end? So this is just asking for you to take the moles of iron and divide by the volume of the solution. So in this case, we're going to take our 1.47 iron iodide, grams. There are 309.65 grams in 1 mole of iron iodide. So that gives us 0.0047473 moles of FeI2. I'm going to show this step even though it gives you the same answer. So for every 1 mole of FeI2, we get 1 mole of Fe. This is another important step. If we had asked about the iodide ion, if it was still in solution, you would need to think about this. So now we have our total number of moles, which is 0.0047473 moles. And the total volume actually comes from right up here with the volume of the silver nitrate solution. So we know that it is 0.2 liters. So in this case, when we plug this into our calculator, we hopefully get the same thing I did, which is 0.0233736 molar. Now sig figs, there are just 3 in this case, which is 0.0237 molar. Nope, yep, there we are. So what questions do we have about this example? If you have questions about this example, I'll answer that while you're thinking about them. The other thing I want to talk about. So don't forget that this is a limiting reactant problem and a solubility problem. So if the silver nitrate was the limiting reactant and we were talking about silver, the concentration would be 0 because all of it goes into the precipitate. If silver iodide was not the limiting reactant, is the precipitate, but the iron iodide is the limiting reactant, you'll have to figure out how much is used and calculate the excess. So Catherine asks, how do you know that it's 1 mole of Fe for every 1 mole of FeI2? So in this case, I got that information from the chemical formula. So we know that for the chemical formula, it's 1 Fe for every 2 iodines. So if you remember back to chapter 3, we've seen this, and in chapter 4, it was this, because it has a subscript of 1, means there's 1 mole of iron for every 2 moles of iodide, or 1 Fe for every 1 FeI2. Does that make sense? So Avery asks, so the 24 millimolar is not relevant in this case? It's not. It could have been relevant. It's important to make sure that you don't just kind of like skip over that. But in this case, because we had a balanced equation and we knew that it was going to be soluble, we did not need that. So yes, it was irrelevant. Emily asks, how do we identify which solids are soluble again? In the chapter 4 slides, in the 4.2 section, I think, there is a solubility table that you can use. In Alex, they have a solubility matrix, which is like a lot, but you can basically look at that. The important thing with the solubility table, and I did not bring one with me today, and I don't think I can pull one up easily, is to make sure that in the top half, the exceptions are insoluble. In the bottom half, the exceptions are soluble. And I think I talked through that in that video. If you're still having questions, I have office hours on Friday morning. Feel free to pop in and we can talk about it. I'd like to highlight Sarah's comment that showing your work, including a balanced chemical equation, is always worth points, even if it doesn't say it. So, Jordan asks, can you explain the limiting reactant thing? Totally. So we have 1.47 grams of iron iodide and 200 mils of 24 millimolar solution. So you could have calculated the moles here and the moles here. Depending on what it asks for in these types of questions. So I have seen everything from a precipitate, so let's think about what would have happened if they had asked about the iodine concentration. So from here, the iodine goes into the solid product. So we want to know, is there excess iodine or not? If it's the limiting reactant, there is none left in the solution. If it's the excess reagent, you have to calculate how much is put into the solid and how much is left over. When you guys see these objectives, this will all make more sense. I only brought one of these examples today. If we finish early and someone reminds me, we will make up another one of these or just pick something else. We'll just change the ions out and solve those questions together. But it's basically, what I want to remind you is that when you're provided quantities of both starting materials, you have to remember that it could be a limiting reactant problem. Any other questions? If you have none, write none on this particular example. Jordan asks, are we allowed to use the solubility table on the exam? So unless something changes, and that does mean that if I keep finding all of our materials on Chegg or any other website, you will be able to use your notes. In your notes, if they include a solubility table, you can use one, but I will not provide one on the equation table packet. So my suggestion would be to print out the notes, because if you print them, they're in the notes. So long answer, short answer, yes, please use a solubility table. So this is a long question, and I'm going to move this over here so that we can all read it. I'm going to erase the board so I can read it. So number 4 says, a chemistry student needs to standardize a fresh solution of sodium hydroxide. He carefully weighs out 1.28 grams of oxalic acid, which is a diprotic acid. In this case, it is strong, and dissolves it in 225 mils of distilled water. The student titrates the oxalic acid solution with his sodium hydroxide solution. When the titration reaches the equivalence point, he's used 17.3 mils of sodium hydroxide. What is the concentration of the sodium hydroxide solution? So, this is a lot of words. This came directly, this was modified out of Alex. I will tell you that your weekly assignment will be something like this. So, the trick is, in a titration, number 1, it's always the first step, balance chemical equation. So let's start with that. So, it does provide the, somewhere over there, the chemical formula, so we're going to start with that. So we have H2, and we know it is sodium hydroxide. So if you remember back to the acids and bases video, diprotic basically means there are 2 protons that come off. It's going to, in fact, be these 2. So we're going to end up with Na2C2O4. So we know if you lose 2 protons, it is basically +1, +1. So this C2O4 is a -2. So we have sodium oxalate plus H2O. Now we need to balance this. We have 2 sodiums, which gives us a 2 here. And we're going to create 2 moles of water. So we have a question. Jordan asks, what does standardize mean? So in chemistry, we often want to know that we have the right thing. So in this case, the student basically, the way I often present this is the student found a bottle of sodium hydroxide and he wants to know the concentration. So we can determine concentration of acids and bases in one of 2 ways. You can make it, and then you know. So you dissolve some grams per mil, or grams per liter, converted to moles per liter, gives you concentration. Or you can use a standard, H2C2O4 in this case, and you can use that to determine the equivalence point. Once you reach the equivalence point, you can determine the concentration. So what we're going to do is, in this case, we are provided with a weight over here of 1.28 grams of H2C2O4. And we need to convert that into moles. So the molecular weight of oxalic acid is 90.04 grams in 1 mole. Now, we have the number of moles of oxalic acid. You could then go ahead and determine the concentration. You could do that. It turns out that we just need to know the moles. So when we have the concentration, we directly convert to moles. Have the moles of oxalic acid. So now we're going to convert to moles of sodium hydroxide. So for every 1 mole of H2C2O4, we need 2 moles of NaOH. So that gives us 0.0284 moles of NaOH at the equivalence point. So now that we've reached the equivalence point, it asks, in fact, what is the concentration of sodium hydroxide? So it tells us that we use 17.3 mils. So if we divide the moles of sodium hydroxide in that quantity, divided by that volume, which is 0.0173 liters, we get a concentration of 1.64 molar. Questions, thoughts, concerns? How do we feel about this one? As always, if you are like, oh yeah, I got it, go ahead and write that in the box so that I know. So before we talk about that one, so Catherine asks, why don't we need the 225? So you might need that under other conditions, but in this problem, that information is irrelevant because we know how many grams you started with and the fact that he used all of the 225 mils. So in this case, it is totally irrelevant. If they give you a mass at the beginning, the volume it's dissolved in is irrelevant. So Holly asks, the volume at the end is the volume of sodium hydroxide. So this is kind of a tricky point, in my opinion. So the volume is always the volume of the object that you're studying. So if you had used the total volume, it would not actually be the molarity of the sodium hydroxide solution. That would be the sodium hydroxide concentration in the whole thing, which isn't what it's asking. Sometimes it does, but in this case, it's not. So this is always just, make sure if it's moles of sodium hydroxide, it should be liters of sodium hydroxide or anything else at the same time. Oh, I'm glad you like this one, Camille. I'm trying to give you guys a variety. Perfect. So now that, I don't want to say that concludes chapter 4, but it does today. So if you missed the very beginning, I talked about how the oxidation numbers and activity series, we're not going to talk about that a lot in this class. They will probably be on the exam, but very basically, to be honest. Titrations are much more exciting, much more interesting. So make sure you watch the videos, but you will see both of those topics, the activity series and the oxidation number in lab. So that information will help you in the labs, which I don't know when that is, but you'll see it when you get there. So now we're going to start to shift into chapter 5. So chapter 5 is about energy. And so in this question, it asks, when you scuba dive, your lungs are under constant pressure of 1.65 atmosphere. Each breath requires 856.6 joules of work to expand. So what volume of air in milliliters is exchanged in one breath? So that we don't have to look it up, here is the unit conversion that we're going to need. So the trick in chapter 5. So I gotta find a new word because I don't really love the idea that it's a trick. Maybe we can think about it more like the treat. This is Halloween-y. So the object here is to figure out what equation to use. Most of our equations in Gen Chem 1 are pretty basic. Take these two things, multiply, divide, add, subtract. But in chapter 5, we're starting to get more equations. So I think the exam 2 or a version of the exam 2 equation sheet is up on Canvas. There will be an updated version for this year, so that will come out not till the end of next week. But when it's ready, you'll get it. So we got to write down what we know, and then we can look at the equation sheet. Or you can look at this and be like, oh, obvi, I know what's happening. But maybe you don't know. So in this case, I always like to start by writing down what I know. So if I panic, I can look at my equation sheet and frankly look for an equation that has some stuff in there. So we know that work is in the question, and it's 856.6 joules. So the other thing, in the video, it talks about assigning the signs, whether work is negative or positive. So in this case, work is going to be negative because we are assuming that the lungs are doing the work on the surroundings to expand. Basically, it's breathing out. So then it gives us a pressure of 1.65 atmospheres, and it asks us for the change in volume, so let's just write down delta V. And that's what we're looking for. So on the equation sheet, or if you memorize the equations, which you definitely don't have to, I will give them to you. We're looking at work equals negative P delta V. So a lot of times what we see is we solve for work. How much work does it do? But in this case, our scuba diver's underwater, and it's asking how much displacement is happening. So we have work equals negative P delta V. Okay, well, let's just see what happens. We start with negative 856.6 joules equals negative 1.65 atmospheres times delta V. So one of the things you might notice is joules and atmospheres are not in fact the same unit. So we're going to use a unit conversion. Unit conversions are the same thing we saw in chapter 1, where you could convert inches to centimeters. In this case, it's that 1 liter atmosphere is equal to a 101.3 joules. That too will be provided for you, not in the problem, but on the equation sheet. So in this case, I'm going to solve for delta V and plug it in like this. Negative 856.6 joules divided by negative 1.65 atmospheres. 101.3 joules is equal to 1 liter times atmosphere. So when you plug this into your calculator, you should get 5.125 liters, and it asks for it in milliliters. So we're going to, in 1 liter, there are 1,000 mils, and our question only asks 3 sig figs. So what we're going to get is 5,130 milliliters. Is the change in volume. So in this case, we never calculated either the final or the initial, but we're looking at what the total changes between the two. So questions? Do we have any questions? If you're like, that was easy, let's see what number 6 is, let me know. I'll give you guys a little bit longer just in case you have a question. We have a couple of more like this. We're going to do some other calculations. I am going to actually reorder the questions. Maybe not. We'll leave them in the same order for now. So Camille asks, how did you get a negative 1.65 atmospheres? So that came out of the question. So the equation is work equals negative P delta V. And so this negative, when I divided by that, I brought it with it. So that's a great question. So it's not really a negative pressure. It is, in fact, just that the whole question is negative. Would scientific notation? Yes. I tend to not think about things in scientific notation, but I will always accept answers in scientific notation. So good question. Any other thoughts before we look at number 6? And I'll try to stop crinkling this paper. Let's go ahead and throw that one up. Ooh. Nice. So in this question, it asks, the temperature of a water bath is monitored and is determined from the data that 307 kilojoules of heat flows out of the system during a reaction. The system has a piston, so it shows that the piston does 487 kilojoules of work on this system, The piston does work on the system. What is the change in energy of this reaction? So we know, or we're learning perhaps, that the change in energy, delta E, equals Q plus W. So it's a good sign. So in this question, we can see heat and work. Nice. So Q equals and work equals. So when we look at our question, it says 307 kilojoules of heat. And it tells us that 287 kilojoules of work. Now, adding two numbers together isn't the hard part of this question. The hard part of this is, in fact, determining whether Q and W should be positive or negative. So let's hope this works the way I think it's going to. Yes. So, all right, I'm working here with this, what we got. So this slide came out of your notes. I made this table because I think it's really clear. So 307 kilojoules of heat flows out of the system. So we look over here, we have heat. Does it go into the system? Nope, it goes out. So heat leaves the system and goes to the surroundings. So that is consistent with what the question asks. So this tells us that Q is negative. And then we can do the exact same thing for work. So the piston does 287 kilojoules of work on the system. So in the work, let's use the mouse. Actually, I don't know if you can see the mouse, so this may not be helping. So the work is done on the system by the surroundings, or the system does work. So the piston does work on the system, so that makes it positive. So delta E in this case is going to be negative 307 plus positive 287 kilojoules. And so when you plug this into your calculator, you should get negative 20.0 kilojoules. Yeah. Well, it's 20 point, decimal point, not 0.0. Oh, Yahtzee. Well, it's not working quite the way I intended. There you go. So what questions do we have about this question? And you might be asking, Dr. Malcolm, did you do your sig figs right? I did, because this is addition and subtraction. So it's about the number either before or after the decimal point. And so 307 and 287 both have, they stop at the decimal point. So you can't go any past that, or you could go before, but that's not really relevant. Questions? Thoughts? Is it easy peasy? We got a none? Yes. All right. So I am going to make the table go away. Whoa, whoa. So we're going to do another question kind of like number 5. We will do another one like number 6 on number 9. So trying to make sure we see all of our options here. So in this case, a mixture of krypton and hydrogen gas is expanded from a volume of 82 liters to a volume of 95 liters, while the pressure is held constant at 36 atmospheres. How much work is done on the gas? Okay. And we know, and it would like it in kilojoules. 1 liter atmosphere equals 101.3 joules. However, Genevieve's question just came in, and so the answer is no. So Genevieve, it's not 20.0 because in addition and subtraction, it's not the total number of sig figs. It's actually the number after or before the decimal. So these two, you can't go past the decimal point, which would be here, on both of these. So in this case, it's 3 sig figs plus 3 sig figs goes to 2 sig figs because you can't move past the decimal point. So in this question, it's going to be work equals negative P delta V. So that's the equation we're going to work with. So once we know the equation, we can look back at our question and then try to figure out what the answer is. So the pressure is constant at 36.0 atmospheres. We also need delta V, which is VF minus VI. So the final minus initial. And so we know that it goes from, so that makes it the initial, so it will be 95.0 minus 82.0, which would give us 13.0 liters. So now I have a pressure and the change in volume. So from here, we can plug it into our equation. So work equals, yep, still in the question, negative 36.0. Hold up, I gotta move over, I'm gonna run out of space. Negative 36.0 atmospheres multiplied by the change in volume, which is 13.0 liters. Now, if you multiply these two numbers together, it gives you work, but in the units of liter atmospheres. And it's asking for it in kilojoules. So we at least have to go somewhere past this. So we're going to use our conversion of 1 liter atmosphere is 101.3 joules, which gives us negative 47,408 joules. But the question asks for it in kilojoules, so from here we can divide by 1,000. And trim back our sig figs, so we will get negative 47.4 kilojoules. Questions? Complications with this calculation? Thoughts? If you're like Dr. Malcolm, this is easy. Feel free to write that in the box. I love to hear that. I will go ahead and put up the next question. Take down number 7. I'm not seeing a lot of questions or comments or thoughts. This part of chapter 5 is significantly easier than what we will see next week. Next week is probably pulling all of the early stuff of 5 together. So with question number 8, 8 is going to be really helpful as we move forward. Yes, easy. My favorite. Oh, don't make me so happy today. So number 8. This part, we're going to see it again in the rest of chapter 5. So the work calculations and the change in energy, we're not going to see that a lot when we start to do the next part of the chapter. So those are often, I don't want to call them easier calculations, but they are easier than what we're going to do in the next part. That isn't to say that the next part is hard. It is just more than multiply 2 numbers or add and subtract 2 numbers. So in this question, it says, what is the enthalpy change if 69.1 grams of aluminum hydroxide decomposes in the following reaction? So then we have a provided balanced chemical equation. In chapter 5, you should not, in any of my questions, I will not speak for Alex because we know that they're crazy sometimes. You should never actually be balancing an equation. You should be provided any equations that you need, like chemical reactions. Now, you might have to manipulate them, as you'll see this next week with Hess's law. But in this case, you're provided a balanced chemical equation and the delta H reaction. So delta H is enthalpy. So what we're asking, or what we're being asked to calculate, is what is the change in reaction for only 69.1 grams of aluminum hydroxide. So the first thing we need to do is convert to moles, because that's kind of all we do. Not all, but it's important. So in A, we're going to take our 69.1 grams of aluminum hydroxide, and that is 77.85 grams in 1 mole. So when we calculate the number of moles, we get 0.8876 moles of aluminum hydroxide. So we calculate the number of moles. Good first step. So now it's asking about the change in enthalpy. If you remember from the video, it kind of ends, not on a cliffhanger, because like I'm not that fancy, but it basically says it's per anything in the problem. So what does that really mean? So our delta H is 41.2 kilojoules. Now what a lot of people want to do is just like plop a per mole under there. And that's probably not the best plan. But what we can do is we can say per mole based on whatever we see in the problem. So it's per 2 moles, right? Yep, 2 moles of aluminum hydroxide. So the change in enthalpy is 41.2 kilojoules for every 2 moles of aluminum hydroxide. This information comes directly out of the problem. So anything in the problem, you can basically divide by that and then multiply by the number of moles that you have. Multiply by 0.8876 moles of aluminum hydroxide. So then the change in enthalpy in this case would be kilojoules, and we only have 3 sig figs, which gives you 18.3 kilojoules. So what questions do we have? And if we don't, that's okay too. We'll do it again in just a second, but this time we're going to look at the change for how much water is produced. Do you guys have questions? If you don't, feel free to drop a comment box question or a comment that says no questions. It's not looking like we're getting a lot of questions so far. So if you're like, you know what, I got this. Well, I'm waiting to see if anyone else has questions. Yes. We're next going to think about what is the enthalpy change for 78.1 grams of water. That should say if. This is an endothermic reaction, so you do have to put heat in. And in this case, it just asks for the enthalpy change, so you don't need to ask, give a sign. But it is endothermic because delta H is positive. So for the second part, we're going to do the same thing, but we're going to figure out how many moles of water we have and then basically set up the same thing. So I don't want to say it's not too complicated, but it is very similar to what we just calculated. So the first thing we're going to do, we're going to take our 78.1 grams of H2O. The molecular weight of water is 18.02 grams in 1 mole of water. And so we will get, I didn't actually stop the calculation there. So we'll just continue. You can always stick stuff all the way together. But then we're going to multiply by our 41.2 kilojoules, in this case, per 3 moles of water. And when we do that, we get 59.5 kilojoules. So, because I stuck all mine together, if you take your 78.1 divided by 18.02, this is 4.334 moles of H2O. So this 3 moles here came out of the balanced equation. So it's not always the same, but it is per any quantity in the equation. So if we were being asked about the aluminum hydroxide, in that case, it would be per 1 mole of aluminum hydroxide. So pretty simple, right? I think so, but you know. Questions, comments, thoughts, ease. Sorry. Oops, I can leave that up, but we'll go ahead and my face is going to be in the middle of this. But we have one more delta E equation question. You can't see that. We're just going to take that down. We'll just try that again in a minute. So far, it doesn't look like anyone has any questions, comments, or thoughts. So we will go ahead and drop that and add in our last question for the day. It does not look like we will have time to do more questions from the ALEX objectives, but if you struggle with that, on Friday morning from 10 to 12, I will be in the Zoom link that you can get to from the homepage, and I'm pretty sure that Megan's going to talk about some of that in SI, but she may have moved on to Chapter 5. You'll have to check her email. So this question asks, what is the change in energy for a system that releases 12.4 joules of heat to the surroundings and does 4.2 joules of work on the surroundings? So I'm going to throw up our table. That sounds real gross. I'm going to post the table while I erase the board so you can look at the table. Even today, I always look back at the table when I solve these kind of questions because the question is it's not always the same. The word does isn't the word that's super important. Well, it is, but it's also important what comes after the word does. So this equation is going to be delta E equals Q plus W. And so we're going to solve out of our equation. So the heat is lost to the surroundings, so it's released. So Q is going to be negative. So we're going to have negative 12.4 joules plus, and the work in this case, the system does work on the surroundings. So when the system does work on the surroundings, work is going to be negative, plus negative 4.2 kilojoules, just joules. So when we plug this into our calculator, making sure to keep all of the signs together, we should get negative 16.6 joules. Overall, I feel like the material today is relatively easy if you follow the steps. Don't try to take too many shortcuts. Don't feel bad about looking at the tables. There is an Alex question that is a fill in the table. It's going to ask about the piston and a bunch of other things. Use this table. This table is going to be so helpful. So when you think about that question, ask about each one individually. And I often think like, okay, if the piston goes up, we're pushing against the surroundings. If it goes down, we're pushing on the system. I know this sounds silly, but it helps me help you. Any questions today? If you have none, go ahead and drop that in the box. If you have some, I'm happy to answer them. Otherwise, I will see you guys next week. Same time, same place. It'll be super fun. We will next week talk about the remaining 3 videos of Chapter 5 that will go up later this week. They may go up before Friday. They are ready. I will post them probably tomorrow, so you can watch them if you'd like. If you have any other questions, let me know. Otherwise, I'll see you guys next week. Nice. Y'all have a fantastic rest of the week. And October comes tomorrow. So it's spooky season, which is kind of fun. Mostly I just like saying spooky season. I'm not really into spooky stuff. Any other questions, comments, thoughts? Doesn't really look like it. Y'all have a fantastic rest of your Wednesday. Miss you.